x-intercept, which we know is also a 0 of our function, then we can take that 0 and we can write it as a factor of our polynomial function. And then by looking at what happens around that 0, we can determine if we have one factor of that with that 0, 2 factors, 3 factors, 4 factors. That's called multiplicity, by looking at what happens just hanging out right around that 0. So when we look at a graph like this, before you even start, so you have a little bit of a check for yourself, can you tell whether this is an even degree or an odd degree? Even, because both arms are going in the same direction. So before we even start to try to come up with a possible equation, we know it's an even function, an even degree function. Are you missing something, Sharima? Do you need something? Oh, okay. Because I was going to say I have an extra packet up here if you need it. An even degree function. And what do we know about the leading coefficient that's going to be multiplying either all of the factors or the very first term if we have it in polynomial form? It's positive because your arms are up. So we know our leading coefficient is positive. Okay. So when I see something like this, I usually do this. It's impossible to write this in polynomial form, but I know I can do this. I have some factors. So I see that I have 1, 2, 3 spots where it goes, where it crosses the x-axis or touches the x-axis. So I know I'm going to have 3 sets of parentheses. And I know that I've got to determine what the multiplicity is for each one of those factors. So I put a little square there, because I know I've got to fill it in. And I know that the form for writing all zeros looks like this: x minus, x minus, x minus some number. So we can just put C1, C2, C3. Later on today, you'll see why we use the letter C for the zeros. Okay, and then I say, all right, can I identify what the zeros are? So the zeros of this function are -2, 0, and the number 1. So I go up and I fill in each one of those factors with each one of those values, and I say, okay, x take away a -2 to some power, x take away a 0 to some power, and x take away 1 to some power. And then I clean this up a little bit. I simplify it. I say, okay, I can write x take away -2 as x plus 2 to some power. X take away 0 I can write as x, so that simply goes out front. So, and then I have x minus 1 to some power right there. Okay, so now the only thing I've, oops, and I still have to put x plus 1 with a little box there. So now I have to determine, are all of these, what are the values for all of those little exponents or powers? So to do that, I take a look at each one of these zeros and I look at its behavior near the x-axis. So let's bring in our magic pen, if I can find it here. Tools, magic pen. All right, so let's blow up this area right around -2. There we go. So that's all we're going to focus on right now, is what's happening right in here. So there we go. Let's make it a little bit bigger. So the first thing you say is the function is going through the x-axis. It's changing sign from being a positive value to a negative. So that tells you the number has to be odd, because all you have to remember in your head is some of your basic functions. A linear function goes straight through, a parabola touches and just turns around, and your cubic goes straight through as well, except that it flattens out a little bit. It doesn't go straight through on a straight line like your linear does. So you can see here, this is mimicking a cubic, because instead of it coming boom straight through -2, it's flattening out just a little bit. It's getting smaller and smaller until it gets to 0, and then it starts growing again. So this has got a multiplicity of 3. So where you see x plus 2, you put the multiplicity of 3 in there. So where I see x plus 2, I'm going to replace it with a 3. Let's put that in a different color. 3. Okay, now I take a peek at what's happening around my other 0, which is the origin. So let's take a look there and see what's happening there. So I just put my little magic pen right there, and I make it a little bit bigger. And if we were just looking at that graph right there, would that look like a linear, a quadratic, a cubic? What would that look like? Linear. So that says you only have one factor of x minus 0 or of x. So where you see x, you just leave it alone. You don't even have to bother to put the 1 in here. If you want to put a 1 there to remind you, you can. Doesn't matter. So if you want, you can put a little 1 there. Okay. So now let's take a look at what we talked about earlier. We know this has to end up being an even degree. And when our polynomial is in factored form, to get our overall degree, we have to add the multiplicities. We have to add the powers. So we've got 1 and 3 here. We're already even, right? So it's not possible for this last one to be an odd number like 1, 3, or 5. So this last one has to be something like 2 or 4 to remain an even number. So let's take a look at what's happening around the 0 of 1. So let's take a look there. I just got to get my magic pen up here forever and ever. Oh, there it is. Oh. So then you zoom right in on here and you take a peek at what's happening around 1, make it a little bit bigger. And what kind of function does that look like? Parabola, quadratic, right? It's the parabola describes the graph. The quadratic tells you what kind of function. It doesn't cross the x-axis. It turns around so you know it's even. And in this case, we're going to say it has a multiplicity of 2. So you put your 2 down here. You check your degree when it's in factored form. Again, your degree when it's in factored form is to simply add up your exponents. 1 plus 3 plus 2 is 6. You're happy because that agrees with your first idea of it being an even function. Okay, so it says give a possible equation. Now, if I knew one other point on here and I knew the values of the coordinates exactly, then I could come up with the exact equation by putting the value of x in and the value for y and then solving for a. But I don't know any other point on here. So one possible equation would be to say a is 1, because I know my arms are going in the same direction. But you could just leave it like this with this condition. If you leave it like this, you have to state that a is greater than 0. And then that's perfectly acceptable as a possible equation. Okay? So that's how you dissect a graph and how you use all the information that you've been accumulating up to this point. You've learned what x-intercepts are. You know that now those values for x make your function 0, so they have a new name. They're called zeros of the function. You also know that wherever a 0 is, it becomes a factor, that when you plug that number in, when I plug a -2 in here, it makes a 0, and so your whole function is 0, because this is all multiplication. When you multiply by 0, everything becomes 0. So these are the kinds of things that we'll be working more with today, except today we're going to say we're going to expand our number system again. And up to this point, we've only been looking at real zeros. These zeros are complex in the sense that we know that complex numbers include real numbers and non-real numbers. So today we're going to expand our graphs to include zeros that are non-real. Before we do that, I'd like to go back and talk to you a little bit about 8b. We did 8a the other day, and we discovered that 8a was not a factor. X minus 2 is not a factor of this polynomial, but we never got to finish this. And so this is where we can start to put together our ideas and see if we're really getting what's going on. So it says to use the factor theorem to factor this. So let's recall what the factor theorem said. The factor theorem said, if you can find a number that you can plug into your polynomial equation and make it equal 0, or your function and make it equal 0, then you know that that value can be written as a factor. So it seems to me that they want us to factor this. They want us to be able to write this as something times something, okay? But I have no idea how to get started. There's nothing that helps me with my regular old factoring kind of ideas that we studied back in chapter 1. So if I have this function, 2x squared minus 3, and I'm trying to find a number that I can use so I can factor it, how do I go about finding that number? What did we call that number? We called the number C. How do I go about finding the number C that will help me factor this? What would I do with this equation? I heard some solve for what? S? Okay, how do I solve for X right now? Put a 0 there, right? Because a factor of a polynomial function is also its 0. So we're trying to say, where does this function have a y value of 0? So I replace this with 0. And now what kind of equation do I have right here that you're looking at? What kind of equation is that? Quadratic. And you hopefully by now can solve these in your sleep. So you can either use your quadratic function, a quadratic formula to solve this, where A is 2, B is 0, and C is -3, or you could factor it. No, you can't factor it. That's what we're trying to do. Or what's your other choice? You have a squared term and a constant term. You can add 3 to the other side and solve for X. So I add 3 to both sides. Now to get to X, I've got to at least get 1x squared, so I divide by 2. And now here's the tricky part. When I do this square root idea of both sides, remember you have two solutions. So when I take the square root of X, I really get the absolute value of X, but we're going to put an X here, and we're going to take care of the fact that it's the absolute value of X by putting a plus and minus out here, and we'll put a square root right over that. Say, come on, Kavanaugh. We're only used to looking at numbers like 2 and -1 and 0. This is a real number, folks. So if we put this into polynomial form, into factored form, remember A times, we've got 2 linear factors because this is quadratic, so I'm not going to have anything higher than a 1 here. I've got an x minus and an x minus, and now I just fill it in with the square root of 3 over 2. So I put, here's my positive square root of 3 over 2. And now when I subtract a negative square root of 3 over 2, this becomes a plus. And there I am, almost done. I haven't completely factored this yet. What am I missing? The 2. Remember, the leading coefficient here of this is a polynomial in the form that we're used to seeing it with all a bunch of terms, adding and subtracting. The leading coefficient here is 2. Guess what? It's the same leading coefficient in factored form. So now you can call this 2 times x minus the square root of 3/2 times x plus the square root of 3/2. And you can check it, because when you check it, it's got to come back to 2x squared minus 3. So you say, oh no. But look at these two factors. These two factors are conjugates of each other. Remember, they look exactly the same except for one subtraction and one's addition. So you have no middle term because your middle terms are opposite. So you just square your first term, x squared, and you square the square root of 3/2. And when you do that, voila, you just get -3/2. The 2's out front. Now you use your distributive property, and you get 2x squared minus 2 times 3/2. The 2's cancel, and you get 2x squared minus 3. So all the ideas work even with yucky looking numbers, like irrational numbers, okay? All the ideas are still the same. You go through the same process. You solve your equation for 0. You find what values of x make your function 0. You throw them into factored form, and then a outside is exactly the same as the a in your polynomial function right here. So if you were starting that on your own, you might start to think, oh, this can't be because I'm getting square root of 3/2. But again, it doesn't matter what kind of number you get. It's still done the same way. Okay. Any questions on that before I move on? Okay, so let's take a look at today's lecture. All right, most of you did not get to a lot of this activity here. So between this activity and today's activity, I'm going to try to keep today's demonstration short so that you can begin working on these two activities for yourself today. So let's take a look at more work with polynomial zeros. And when we're finding zeros of a polynomial, the question is, what kind of numbers can I get for zeros? Now, up to this point, you've only gotten sort of like either integer values, maybe some rational numbers, and you just saw an irrational number, square root of 3/2. But here's a polynomial that's completely factored with all of the different possibilities of zeros that you can have. So as you look through here, what are the zeros? Can you identify just one zero at a time? Anybody can tell me one zero here? Karen? Oh, 3. All right, so were you looking at this first one right here, Karen? All right, so x plus 3, you ask yourself when that equals 0. -3. Okay, so we've got -3. That's 1 0. All right, another 0. 1/2. And how'd you get that? You took 2x minus 1 and set it equal to 0, Jasmine. Okay, and when you do that, you get x equals 1/2. That's correct. So we got 1/2. Okay. Now let me wipe. Okay, and then so we've taken care of the first two. Next one. Negative square root of 2. We've got x plus the square root of 2 equals 0. And guess what? We've got its partner right here, its conjugate partner right here. So that tells you you're going to have a plus square root of 2 and a negative square root of 2. So we've got positive square root of 2 and a negative square root of 2. Okay, because we're looking at those two right there. Okay, and then finally, what do we have left? Do you see an x minus 1 anywhere? I don't see an x minus 1. Where did you get the 1 from? Looking over here, Anna? From looking over here? Okay, so first of all, what do we, our zeros always have this form here. So what am I subtracting here? -4 plus 5i, right? So if I put, no, I'm subtracting not -4, I'm subtracting 4 plus 5i, right? Just like out here, you know, right here, right? You say, what would make this 0 another square root of 2? What would make this 0 a negative square root of 2? Because if I wrote it in subtraction form, it looks like this, negative square root of 2. Okay? So you put your little, there's your subtraction, you put your little brackets around there, and you say, yeah, if I put this exact same thing in here, 4 plus 5i, and I subtract 4 plus 5i, will I get the same thing? Well, let's see. Well, let's just set this whole thing equal to 0 and see what we get. I set the whole thing equal to 0 just like we always do. All right, so we're going to solve for x. No big deal. I've got two terms here hanging on to x. So I add 4 to both sides. X plus 5i equals 4. And now I got to get rid of minus 5i from each side. So I get x equals 4 minus 5i. And that's what x becomes. So we have 4 minus 5i. And in a minute, you'll see once you get one of these non-real zeros, you got the other one automatically. So now let's set this equal to 0. So we have x take away 4 minus 5i. We want to set that equal to 0, right? So what do? We add 4 to both sides, right? And we add 5i to both sides. So we get 4 plus 5i. So just like these irrational roots, if you have 1, you have the other because they just changed sign. So if you change the sign of this, their conjugates, the negative, the subtraction sign becomes an addition sign. So you can look at this and say one of your zeros is 4 plus 5i. That actually is the 0 for this one. It's a little tricky because if you put 4 plus 5i in there and you subtract 4 and you subtract 5i, that gives you a 0. But once you can identify one of them, you can get the other one because they're just conjugates of each other. And all that means is the addition changes to subtraction, or subtraction changes to addition. Okay, so these always come in pairs. Always. They always come in pairs. So if I tell you you have a polynomial that has a 0 at 4 minus 5i and I say nothing else, you automatically know your other 0 is 4 plus 5i. And often your book or on a quiz or a test, it is not written that you have 4 minus 5i and 4 plus 5i. It's only going to tell you one of your non-real roots. These always come in pairs as well. Okay, so let's take a look and classify each of these. -3 is a real number. And can we be any specific? It's real, it's rational, and what other kind of number is it? Negative, yep. Give me an I. Integer, right? It's an integer. Okay, 1/2 is real. Is it an integer? Is it an integer? Some of you discovered that on your last project, the transformation project, when I said use only integer coefficients and you put numbers in like 3.5, that's not an integer. This is just a rational number, a ratty number. Okay. Square root of 2 is real. What kind of number is that? Irrational. Negative square root of 2 is real. It's also irrational. 4 minus 5i, non-real. Non-real. And all of these numbers, all of these zeros are considered complex. We call real zeros, you know, we usually divide them into real zeros and non-real zeros, but you could say all of them are complex zeros. Because whether you're a real number or a non-real number, you belong to this big group called complex numbers. Okay, so that's just identifying some language we're going to use for today. And now, how do we figure out the degree of this polynomial that I've written right here? How do we figure out the degree? Did I hear something from back there? No? I heard something. Yeah, just add up these powers all the way across on each factor. So you have a 2, you have a 1, you have a 1, you have a 1, you have a 1, you have a 1. So 2 plus 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5. It's 6th degree. 7? 1, 2, 3, 4, 5. Ooh, thank you. 7. All right. How many linear factors do you see? How many linear factors? Those are the ones that have degree 1. You said 1, 2, 3, 4, 5. You have 5 of them. All right. How many zeros? Now, this is where you got to be a little careful. How many zeros? Is this true? I have 5 linear factors. You let me get away with that? I've written this in a compact way, but if I wrote it out, how could I write x plus 3 squared out? X plus 3, x plus 3. And if I did that, how many linear factors would I have? If I wrote this out the long way, x plus 3, 2x minus 7, right. So folks, if you don't write it out using exponents compactly, then your number of factors is exactly the same as the degree of your polynomial, and the number of zeros you have counting multiple zeros separately. What do we mean by multiple zeros? That is anything that's raised to a power other than 1. So if you wrote this as x plus 3 times x plus 3, you would have a 0 of negative 3, and you count it twice. So you have negative 3 2 times, and all the other zeros here are counted once. So you have exactly the same number of zeros as your degree and as your number of factors. So this is a little different than what you learned a few days ago when you said at most you can have n minus 1, at most n real zeros. We had the word real in front of it. Now it's complex zeros. And if you consider both real and non-real zeros, then the number of zeros, the number of factors exactly match your degree. Always. When you open up your system and include non-real numbers. Okay? So all these numbers should match when you're done. Let's take a look at one of these. So here's a function, x cubed plus x squared minus 5x minus 2. Be careful, this is not in factored form, it's in polynomial form right now. So when it's in polynomial form, how do we find the degree? When it's in polynomial form, you look for the highest exponent, right? So what's the highest exponent here? 3, so this is a cubic. So this is a cubic function. Its degree is 3. So before I even start, how many linear factors, if I wrote it all out without any exponents, how many linear factors will I have? 3. How many zeros will I have? Real and non-real? 3. Okay. What's my leading coefficient in my polynomial form here? 1. So all I'm thinking of right now in my head is a set of parentheses, a set of parentheses, a set of parentheses. 3 sets of parentheses with a 1 out front, and I'm going to find the zeros, and I'll completely factor it. So to find the zeros of a polynomial or any function, we set the function equal to 0 and try to solve. Why? To find the zeros of a polynomial for any function, so here's our function. We set the function equal to 0. Our function is f of x. We set that equal to 0. Why do we do that if we're trying to find the zeros? I mean, it's kind of a silly question that I'm asking you here because the answer is kind of given. So why do we set the function equal to 0? The y-intercept? X-intercept, right? When we find the x-intercepts, we find the zeros of our function, and we find the factors of our function. They're all come in one tightly closed box here. Use your graphing calculator to find one nice integer value 0 of this function. Well, I did it for you because I knew we wouldn't have, we used to have graphing calculators be required for the course. So here's a picture, and I'll get some graphing calculators for later. And it tells you right here that one of the zeros of this function is x equals 2, y equals 0. So I have found one nice integer value 0, x equals 2 is my integer value 0. Now I have a 0 of the function, so I also have a factor of the function, 2 for the price of 1. So what's my factor going to look like? If 2 is a 0, what would factor x minus 2? So I now can use polynomial division to get the other factors. So I'm going to divide this polynomial, x cubed plus x squared minus 5x minus 2 by x minus 2. And you can either use long division or synthetic, because this is the problem with synthetic is that your factor out here always has to have this form, x take away some number. So if you have a factor different than that, you could be in trouble. So x goes into x cubed, x squared times, I multiply. I subtract both of these, so I change both signs. Now I have 3x squared minus 5x. X goes into 3x squared 3x times. 3x times x minus 2 gives me 3x squared minus 6x. I change both signs to subtract. I get x minus 2, thank goodness. When I get x minus 2 and I multiply 1 by the divisor x minus 2, I get exactly the same, and I get a big happy face because I know x minus 2 is going to divide that evenly when I do my long division because I've been told it's a factor. So now I can rewrite this. My leading coefficient is 1. I know I have one factor called x minus 2, and here's my other factor, x squared plus 3x plus 1. But I haven't completely factored it. I want to completely factor this. So to completely factor this, I have to be able to factor the second factor right here into two linear factors, because that's always our goal, to keep factoring. So how am I going to factor x squared plus 3x plus 1? There are no factors of 1 that add up to 3, so I can't factor it using my normal means. So, quadratic formula, right. So let's use the quadratic formula on this to find the solutions to this equation. That's what the quadratic formula does. If you're finding the solutions to this equation, you're finding a 0 or 2 zeros. So x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's -3 plus or minus the square root of 5 all over 2. So there are my other zeros. 1 0 looks like this, -3 plus the square root of 5 over 2, and its partner comes along. Its conjugate is I just changed that addition to minus. So its partner looks exactly the same, except I have a subtraction sign. So this becomes x takeaway, and now I use parentheses in here, -3 plus the square root of 5 over 2, and x take away -3 minus the square root of 5 over 2. Now I'm done. I've completely factored that. So the 3 zeros are 2 and plus and minus -3 plus and minus the square root of 5 over 2. There are my 3 zeros, and here it is completely factored. So now you're going to get numbers that, again, I mentioned earlier, can be irrational numbers as well as rational, and they also can be non-real complex numbers as well. We've already answered this. The degree of the polynomial is 3 because we have 3 linear factors and we have 3 zeros. Everything's the same. 3 linear factors, 3 zeros. 3 is the degree of the polynomial. So the only change now that you could imagine is, let's suppose I use the quadratic function on a second degree trinomial like this. I could end up with complex results, imaginary numbers, non-real complex numbers. Okay, that's the only change that we can have here. So here are your conclusions. I want you to read this. I'm not going to read it for you. It's there. It gives you all of the ideas about what we can now conclude about any polynomial function. And now I just want to do this last one with you before you take some time to do your activity. It says find a third degree polynomial function. So the minute you see that third degree polynomial function, you immediately, I don't even have to go any further. This is what you should write down on your paper right away. See why we use the letter C now for our zeros? Because we're dealing with complex numbers. That's why they use the letter C. That's what I can write right away. I know I'm going to have 3 linear factors. It may be true that some of these factors may be the same. I'm going to have 3 zeros. Maybe they're not all distinct. Maybe they are. And I know that I have a leading coefficient here of A. Now, it says here with real coefficients that has a -3 for a 0. So if one of my zeros is -3 and I work backwards to get 0, By adding 3 to both sides, what's my factor look like if negative 3 is a 0? X plus 3, because I just add 3 to both sides to get back to my factor, x plus 3. So I can go right up here and I can write x plus 3. Wow, that was good. I've got one of these done. Okay. Now it says, and it has I as a 0. So if x equals I and I go back one step, what would I have to do to both sides here to get a 0 on the right side? What would I have to do? What would I have to do to get a 0 here? Subtract I from both sides. Right, you're just working backwards to your factor, x minus I. So there's my other factor, x minus I. Because if I put an I in here for x, I minus I is 0. Cool. All right. Now, I don't have enough information to finish this off. How am I going to get my other 0? No point's not going to help me if I don't have this value C3. Remember, they come in pairs. I just told you a second ago, we're not always going to tell you. If I is a 0, what else is a 0? Negative I, right. So if x equals negative I and you go backwards, you get x take away negative I, which is x plus I. So that's your very last one here. There we go. So, and if that's all the information I gave you, that's all you could do. But I gave you one bit of information. I told you a point that's on this graph. What's that point, Andre? What are the coordinates of 1, 8? So where I see x, I can replace it with 1. And where I see f of x, I can replace it with 8. And now I can simplify this. So I'm just going to move down a little bit here. 8 equals a times 4. And what happens when I multiply these two things? 1 minus I, 1 plus I, they're conjugates. So I get the difference of two perfect squares. I get 1 square minus I square when I multiply these two. And that gives me 1 minus a negative 1, because I square is negative 1, which is 2. So this is what I get. 8 equals 8a, and I've got to do all that just to discover a is the number 1. So when I factor this out, it looks just like this. F of x equals 1 times x plus 3, and then the two factors, x minus I, x plus I. If you have an x minus I, you'll have an x plus I. If you have an x minus 2i, you'll have an x plus 2i. They always come in pairs, and their signs, their operations are opposite. So you'll have a lot of opportunity here with your activities to practice all of this polynomial stuff. Remember, some of this stuff starts on page 9 and 10 of your last activity, and today I've given you a couple of more on page 14 and 15. Why don't you try one from today, 1 or 2 from today, and then go back and see if you can finish up a couple from the other day. It'd be good to practice the ones you think you have the most difficulty with, maybe like working with the non-real zeros, like 3 plus I, 3 minus I. And I can help you out.